Hello everyone. Today we are going to talk about chapter 9, 9.1, Introduction to Linear Higher Order Equations. Okay, so previously we have linear first order equation, right? So we knew the form, right? Okay, how about linear second order equation? So we had a form like that, right? So y second prime p of x, y prime q of x, y equal to f of x, right? How about linear higher order equation, like this section title, right? So we have nth order differential equation, yeah? So we have y to the n power as p sub 1 over x y to the n minus 1 derivative, not the power, y to the n derivative, and y to the n minus 1, and p sub 2 of x, y to the n minus 2 derivative, then y to the first derivative, and the last term is just y, yeah? And then y side, the same as f of x, yeah? Okay, now, so we have a polynomial left side. So p over x and y to the n derivative and so on, right? Equal to f of x. Look, then we say that this left-hand side, because this is too long to write, right? So make it short as sub L sub y, yeah? So we have the left-hand side linear. So we are using the first letter, linear L, and higher order equation, right? So we have this form. Yeah, that's why we using in terms of y of higher order derivative, right? That's why we are using not L, L sub y. Make sense? Okay, now they say that left-hand side, same as right-hand side, is normal on between A and B, open interval A and B. All right? Okay, now what is a normal? Yeah, let's take a look. So we have a theorem. Suppose the left-hand side, which is linear higher order equation, is the same as right-hand side, f, is normal on open interval A and B. Let x be point in that open interval, then we have the real numbers, k sub 0, k naught, k sub 1, until k sub n, right? Real numbers, any arbitrary real numbers. Then we have initial value. So y over x naught equal to k naught, y prime over x naught equal to k sub 1, and so on, has a unique solution. Yeah, makes sense? So we have left-hand side equation, which is linear higher order equation, same as right-hand side, the function. Then with the initial value problem, right? Then there is a unique solution. We called normal in continuous open interval. Yeah. Okay. Now we have homogeneous equation, right? So we had this one before. Homogeneous equation, other side equal to 0, right? Okay. Then they say that left-hand side equal to 0, then we have a trivial solution. So we had a trivial solution before, right? What is that? That's a zero solution, right? So we can use the y of x equal to 0, 0 solution, right? And I forgot to mention that from the left-hand side, then look, we don't have a piece of 0 here, right? Yeah, this means we divide by piece of 0 every term, but then why we still have a piece of 1? So mathematician get lazy, right? So okay, let make a divide by piece of 0 every term, but this piece of 1 is not same as piece of 1. It's a divide by piece of 0, same as, yeah? So every term divide by piece of 0, piece of 0. Is it clear? Okay, yeah. All right, so let's move on. So if we have y sub 1, y sub 2 until y sub n in the open interval in A and B, and we have a constant, right? Then we have a linear combination form. Yeah, we had to do this one before, right? Is it first time? I think we did this one before, right? Okay, so this is a form of linear combination of y sub 1, y sub 2 until y sub n, right? And we have another terminology, fundamental set. So we call this set is fundamental set of solution of L sub y equal to 0, right? So L sub y, we have a left-hand side equation, right? Yeah, so we don't want to write down whole thing, that's why. So L sub y, basically we include the p naught, p sub 0 there, right? So we say that L sub y equal to p naught x, and then higher derivative over linear equation, right? Okay, all right. Then general solution, we know that, right? General solution. So y equal to c sub 1, y sub 1 plus c sub 2, y sub 2, and c sub n, y sub n. Depends on, right? Yeah. And of L sub y equal to 0 on A and B, right? Okay, linear combination. So we have another very important terminology, linearly independent, right? So everything, those terminology from linear algebra course, right? That's why differential equation prerequisite is linear algebra. Yeah, okay. So we have y sub 1, set of y sub 1, y sub 2 until y sub n is linearly independent. Then we have a scalar, which is constant. Then we can express this one equal to 0. Yeah, trivial solution. Yeah. Then we get c sub 1, all the constant, all constant or 0. Yeah. All right, then we call that is linearly independent. All constant are 0. That's linearly independent. If there is at least one, it's not 0, so not all 0, then we say that the set of y sub 1, y sub 2 until y sub n is linearly dependent, right? So every time we have opposite definition, right? So we had trivial solution, then homogeneous equation, then what's the opposite? Non-homogeneous, non-homogeneous equation, right? And we have a trivial solution. What's the opposite? Non-trivial solution, right? Yeah. And we have linearly independent. What's opposite? Linearly dependent, right? Yeah. Okay, so we understood, right? All right, then they say that another theorem, we have if the s of y equal to 0 is normal, then set of y sub 1, y sub 2 until y sub n of n solutions of the s of y equal to 0 is a fundamental set. We talked about the fundamental set earlier, right? If only if, so IFF means if only if only and if, right? That means goes to this direction, make a true statement. Also goes to this direction, make a true statement, right? So if only if. So I can read if it's linearly independent on open interval, then this is true, right? If this is true, then this is linearly independent. That is how if, only and if works, IFF. Make sense? Okay, now let's do examples so that we understand everything, yeah? Okay, so we have the left-hand side, L sub y equal to 0, it's normal. Then has the unique solution, right? So has the solution. Y sub 1 equal to x squared, y sub 2 equal to x to the third power, y sub third equal to 1 over x on negative part, and we don't include 0 because of parentheses, right? And positive part, right? Because we have a fraction there. That's why we don't want to include the 0 there, yeah? Okay, now show that y sub 1, set of y sub 1, y sub 2, y sub 3 is linearly independent on open interval, not include 0. That means then find the general solution on the open interval, right? Not include 0. General solution, how it looks like, right? We've been doing, we have been doing this so long time before, right? Before Laplace transform, right? And look, show that it's a trivial solution. Yeah. So what's the trivial solution? All C sub I are zeros, zero solutions, right? We talked. Okay, so let's do it. Okay, I wrote down C sub 1, Y sub 1 plus C sub 2, Y sub 2 plus C sub 1, C sub 3, Y sub 3 equal to 0, right? So this is S sub Y, and then the this one, if we make a y, then there is a linear combination form, right? Okay, now we set other side equal to 0. Why? Because we want to show the trivial solution. That is, all C sub 1 equal to 0 equal to C sub 2 equal to C sub 3. Make sense? All right, so let's do it. Okay. So y sub 1, let's substitute y sub 1 equal to x squared, y sub 2 equal to x to the third, y sub 3 equal to 1 over x. Yeah, okay. So c sub 1 plus c sub 2 plus c sub 3 and y sub 1 x squared, y sub 2 x to the third power, y sub 3 1 over x. Yeah. Then we make a 0. Oh, oh no. Okay. Maybe this one. Oh, okay. Hold on 1 second. X equal to 0. Okay, let's say this is equation number 1. All right, now we want to derivative respect to x. Yeah. So let me copy. So while copying, you think, what's the derivative of that, right? Okay, so that will be derivative of x squared, 2x, and c sub 1, right? Derivative of x to the third power, 3x squared, c2, right? And derivative of 1 of x to negative 1, so drop the power, reduce by 1, so negative x to negative 2, right? Yeah, so I'm gonna write down. So that will be 2c sub 1 plus 3c sub 2 x to the second power minus c sub 3 and 1 over x to the second power, right? Make sense? I don't have to write that, right? You guys good. Okay, so we call this is equation number 2. So this is also, we can say that since we call this is left-hand side, earlier we've been talking about, right? So left-hand side will be, we don't want to carry all the time. That's why we say it, give it to the name, L sub y, right? So in that case, then this will be derivative, right? So derivative of L, derivative, derivative of L sub y, yeah? Okay, now from derivative, left-hand side, let us derivative again, right? So second derivative, yeah. All right, so looking at equation number 2, only this one. Yeah, let me do it. So we want to derivative again. Derivative, right? So I should not talk too fast. Then pronounce is not good. All right. So we want to derivative constant. Oh no, I omit x. Sorry about that. X, yeah. Everything's good? All right. So it's not constant anymore. So we want to derivative. Then this is a 2c sub 1, right? Now the derivative of a second term, 3c sub 2 times 2, yeah? So 6c sub 2 times x, yeah? Okay. Now we want to derivative of a third term. So we have x to the negative 2. Drop the power, so negative, negative, so it's a positive 2, c sub 3, and reduce by 1. So x to negative 3, right? Make sense? Okay, let me write down. So that will be 2, 2 c sub 1 plus 6 c sub 2 minus positive and 2 c sub 3, 1 over x to the third power, right? And then we want to make equal to 0 and say this is equation number 3. Okay, now we want to give it to the name that will be, this one whole thing will be the second derivative of L sub y. Yeah? Good? All right, now from equation number 1, ooh, I want to From equation number 1, from equation number 2, I want to make a whole thing orange here, yeah? So equation number 1, copy. And equation number 2, copy. And equation number 3, copy. All right. So let x equal to 1. We don't want to pick x equal to 0 because we want to show that trivial solution between open interval, right? So in that case, we have a negative part and positive part. So let x equal to 1, pick any number. But 1 is always easy. That's why we arbitrarily pick the 0 sometimes, 1, -1, right? Most of the time, right? 0 to positive infinity, right? Okay, then let's just substitute everything. So what do you get? So we have c sub 1 plus c sub 2 plus c sub 3, since x equal to 1, right? Equal to 0. Equation number 2, so 2 c sub 1 plus 3 c sub 2 minus c sub 3 equal to 0 as well, right? Okay, please correct me if I make a mistake. And third one, equation number 3, 2, oh, there is no x, so 2 c sub 1 plus 6 c sub 2 plus 2 c sub 3 equal to 0, right? Ooh, 3. Okay, look. So we are using constant, yeah? So then we're gonna do that row echelon form, reduce the row echelon form. So decimals. So we are using 1, 1, 1 constant term, 2, 3, -1, 2, 6, 2, yeah? All right, so other side, we make a 0, 0, 0, but in decimals, we don't have to type, okay? So we can omit in the decimals. All right, so reduced, reduced row echelon form. So what do you get? We get 1, 0, 0, and 0 and 0, 1, 0, 0, 0, 0, 1, 0. Okay, so there will be c sub 1, c sub 2, c sub 3. So that is c sub 1 equal to 0. That is c sub 2 equal to 0. That is c sub 3 equal to 0, right? So all the constant term is 0. So it's a trivial 0 solution, which is a trivial solution on positive part because we picked the x from the positive part, which is 1, right? So it's a trivial solution. Since c sub 1, c sub 2, c sub 3, all zeros. Yeah, 0 infinity. Yeah. Okay. you know how to use Desmos, right? Yeah, from the linear algebra course. So we can use matrix Desmos, yeah? So matrix Desmos. Then using 3 by 3 and reduce the row echelon form, there is the notation. So we can set this one is A, then reduce the row echelon form A, then we get the answer. Okay? All right, now let's try x equal to -1 from negative part. Yeah. So try x equal to -1. So pick any number from negative part. Yeah. We cannot pick 0 because 0 is not included there, right? So normally easiest one 0 or -1, +1, right? Yeah. Okay. So same processing. So I want this one so that we can deal with negative, right? In the case. Copy. Okay. So what do we have? -1, right? So we will have first term is a positive, so 6 sub 1. So that will be 6 sub 1, negative 6 sub 2, and negative, so negative 6 sub 3, yeah? Which is equal to 0. Equation 2, negative, right? So negative 2c, positive 3c2, negative c3, 0, right? Okay, now the equation number 3, 2c sub 1, sorry, c sub 1 missing, and plus 6c sub 2, and third term is negative, so negative 2c sub 3 equal to 0, right? Okay, so Desmos, we can use that, matrix Desmos. So 1, -1, -1. We can omit 0, 0, 0 here. And -2, +3, -1, 2, 6, -2, right? Okay, then reduced row echelon form. So we get, I have to conclude. So I want to make a little bit smaller. Too big because I want to make a conclusion. So we get 1, 0, 0, 0, 1, 0, 0, 0, 1. And 0, 0, 0. Okay, so that means C sub 1, C sub 2, C sub 3. So C sub 1 equal to 0. And that means C sub 2 equal to 0. That means C sub 3 equal to 0. Yeah. Okay, so it's a trivial solutions. If we have it's a trivial solutions, negative part, right? So I'm not gonna write down all the system one. The constants are zeros, right? Because I already wrote down earlier, right? So negative infinity to 0. So therefore, how do we conclude? So the set of y sub 1, y sub 2, y sub 3 is linearly independent on, so let me write down the set of y sub 1, y sub 2, y sub 3 is linearly independent on open interval, in that case, negative infinity to 0 and 0 to positive infinity. Yeah. Oh, general solution. So general solution will be y equal to no space, that's why. General solution, y equal to c sub 1, x squared, y sub 1, plus c sub 2, y sub 2, x to the third power, plus c sub 3 over 1 over x. Sorry. Can you see? Yeah. Okay. Now, we have other method. So this is from linear algebra course, homogeneous linear system of n equation and n unknown has only trivial solution if its determinant is non-zeros. Yeah. Okay. So I made a highlighted n equation with n unknowns. That means they have the same size of equation and the variables. Yeah, unknown means unknown variables. Okay. All right. So then we need to show that their determinant is non-zero. All right. Then homogeneous linear system means that we make other side equal to 0 and we can say that L sub y equal to 0, right? All right. Let me see. Hold on 1 second. Okay, so I wrote down this one. So if the determinant is non-zero, then we denote like that, right? Determinant of just any, the matrix is not equal to 0, non-zero, then the matrix is invertible. What this means? This means there is only one solution and each trivial solution. So trivial solution means the zero solution. So C sub 1 equal to 0, equal to C sub 2 equal to 0, C sub 3 equal to 0, right? What about other way, right? So if the determinant of A equal to 0, then there is infinitely many solutions. That means C sub 1 equal to 2, C sub 2 equal to whatever number, C sub 3 equal to whatever number, right? Yeah. There is infinitely many solutions. Yeah. Okay. Now, let's do it. C sub 1, let's bring the equation. And this is the equation, right? We take the coefficient. Okay. Let me see. The original one. Yeah. Okay, so because this is a constant. Let's pick this one. This is better without X. Copy. All right, then we can express same thing. We did that, right? So I'm gonna show you. How about I'm gonna show you this here. I have this one. So using decimals, right? All right. Matrix, decimals. Okay, so I just copy 1, 1, 1, 2, 3, negative 1, 2, 6, 1, 2, sorry. Yeah, take the coefficient. Okay, then we're using determinant of A, which is 12, which is non-zero. So in that case, when x equal to 1, right? So when x equal to 1, okay. How about when x equal to negative 1, right? So we have this one, right? Copy. So when x equal to negative 1, right? Okay, so decimals. I don't have that. Yeah, I don't have. Okay, so you try then determinant by decimals. We are using 1, negative 1, negative 1, and 0, 0. Oh, we don't need that. We don't have to write that, right? Omit. It's okay because we don't have to because we are lazy. 3, negative 1, 2, 6, negative 2, right? Okay, determinant using that in decimals. So determinant using that. A equal to negative 12, yeah, which is non-zero too, right? So this is non-zero, non-zero, and this is non-zero. Yeah, then we can conclude if there is non-zero, there is zero solution, which is trivial solutions, right? So we can conclude that if there is a trivial solution, all constants, C sub 1, C sub 2, C sub 3 are equal to 0, then it's a set of y sub 1, y sub 2, y sub 3 is linearly independent on open interval, right? Yeah. Okay, so let me write down. Let me just conclude, right? Y sub 1, y sub 2, y sub 3 is linearly independent on open interval negative infinity to 0 and 0 to infinity, since in that case the determinant of A is not equal to 0, non-zero. So that means there is all C sub I are zeros. Yeah. So C sub 1 equal to 0. equal to C sub 2 equal to 0, C sub 3, yeah? Okay, now, general solution, right? General solution. So, same, y equal to, don't remember, C sub 1, x sub 2 plus C sub 2, x sub 3 plus C sub 3, 1 over x, yeah? Make sense? Okay, now, this terminology connect to the Wronskian, right? Why? Because if we have determinant of Wronskian is not equal to 0, same as non-zero, then all the constant C sub 1, C sub 2, C sub 3 until C sub n equal to 0. And we have a general solution, not general solution, L sub y equal to 0. Okay, so here we go. We have that. So look, this is what I talked just now. So determinant of Wronskian, right? Then determinant of Wronskian of y sub set of y sub 1, y sub 2 until y sub n. And it's not equal to 0. Then the system has only trivial solution. So let me, Wronskian is not equal to 0. Only trivial solution. That, yeah. Okay, let's do it. And then 2 by 2, we know how to apply Wronskian, right? So 2 by 2 determinant is the same as, right? Yeah. Okay. We have this example. This is the same question earlier, right? And then we just found this is a linearly independent, right? And then we want to calculate the Wronskian of y sub, set of y sub 1, y sub 2, y sub 3. Yeah. Okay. So in 3 by 3, I rewrite this way. Wronskian, right? Determinant. Okay, now y sub 1 is given earlier, right? Oh, here too. So we have the solution y sub 1, x squared. So replace by x squared into y sub 1, x to the third power 1 over x. Yeah. Okay, now this question has combined method. So if we have a 3 by 3, there's a shortcut 3 by 3 determinant we can find, or we can find the cofactor, right? Yeah. And this is, we are using the property of determinant. So combining everything, okay? And then there is a reduction, or what is called row operation too. All right? Yeah, let's do it. So I am following the textbook, okay? But then you can do whatever you like. Yeah, 3 by 3. Yeah, so we factor out x squared for this row. Yeah, so we factor out x for this row. We factor out 2 this row, right? So this is one of determinant property. Yeah. Yeah, one of determinant property say that we can multiply, right? Yeah. All right. So there will be, oh, I do not have it. Okay, then the first row, we have x squared and with a purple. So I'm going to write down x squared with the purple. Then inside we have 1, right? And x squared factor out, that means divide by x squared. We knew, right? So it's x. And then we factor out with the x squared, then that will be divide by x squared. So if we divide by x squared, then there will be 1 over x to the third power, right? So if we multiply back, then we get 1 over x. Yeah, make sense? Okay, now, second row, factor out with the x. That means 2 remaining and 3x squared. Then 3x remaining. Negative 1 over x. That's negative 1 over x to the third power. Sorry, I did not factor out x, right? So let me do x here because we're going to multiply everything. Yeah. Okay, now factor out with the 2 orange color. So we do 2. Then 2 is 1 remaining. 6x, 2x, I'm sorry, 3x remaining, right? And third one is 2 out, then 1 over x to the third power, right? Okay, now what do we do? Okay, so let's say that this is row 1, row 2, row 3, right? So we're gonna make the row operation. So look, all together this will be 2x to the third power, right? Okay, now we're using row 2 plus row 1 to make row 1. Yeah, looking at that, row 2, and we add row 1 to make row 1. This is a 3. This is 4x. And this is 0, right? So 3, 4x, 0. Yeah. Okay, row 2, I just rewrite. So 2, 3x, negative 1 over x to the third power. And the third row, I want to make a row 2, add row 3 to make a row 3. Yeah? So that means 2, 3 add together to make a row 3, right? Okay, that will be 3, 6x, 0. Yeah, okay. So 3, 6x, 0. All right, now we have 2x to the third. Now I want to take out this one, negative 1 over x to the third power. Okay, then we have to be careful the sign, right? So when you take out like a cofactor extension, right? So we have plus, minus, plus, minus, plus, minus, right? So we will have negative, negative is a positive 1 over x to the third power, right? Make sense? Okay, then once we take out, we factor out this one. So we cross out, right? That's a cofactor expansion, right? Yeah. All right. So then what we have a 2 by 2 determinant, right? So there will be 3, 4x, 3, 6x. Okay, now we can easily find the determinant. So we have simplify this one, so we have a 2. And we get 3 times 6x minus 4x times 3, right? Then what do you get? So we have 18x minus 12x, which is 12x. Yeah. All right. So look, we cannot have a 0 there because it's they say that it's on open interval, right? Between here, right? So 0 is not included there, right? So we cannot have a 0 there. That means x for any number besides 0 except 0, right? So we start any number, so it's not we call the non-zero, right? Yeah. So therefore we show that Wronskian, so it's W is the omega because we using W from Wronskian, the first letter W. Yeah, not the omega. Omega make a little bit fancy. Yeah. Okay. X is not equal to 0, non-zero. Yeah, non-zero, that means all we have a 0 solution, right? Okay, negative infinity, 0, and 0 to positive infinity, right? Yeah, so note, can't have x equal to 0 since 0 is excluded. Yeah, x is not included. All right, so we done. Thank you for watching. Bye.